Hello everyone, in this video we will learn about the adjoint of a square matrix, the properties of adjoint of matrix, singular matrix, non-singular matrix and the inverse of a matrix, how to find out the inverse of a matrix by using adjoint. Let's learn about the adjoint of a square matrix first. Let A be a square matrix of order n into n, where n is greater than 1. Suppose A is represented as Aij, means Aij are representing its elements. Then its cofactor matrix is represented as Cij, and that will have all the cofactors Aij of all its elements. We have already learned how to find out the cofactors, where Aij is the cofactor of Aij. The transpose of Cij, that is Cij dash, is the adjoint of A, and it is represented as adjoint A, or we write as ADJA. It means we can say that adjoint of a matrix A is the transpose of its cofactor matrix Cij. Suppose we have a matrix A, and that is A11, A12, A13, A21, A22, A23, A31, A32, A33. This is of order 3 into 3. Then we can say its cofactor matrix Cij is having all the cofactors of all the elements of it, and we represent the cofactor by Aij. So we can write that it is A11, A12, A13, A21, A22, A23, A31, A32 and A33. Then the adjoint of A will be the transpose of Cij, and that will be A11, A12, A13, that will come in column. A21, A22, A23, A31, A32 and A33. For example, suppose we have a matrix A of order 2 into 2, and the elements in this are 2, 3, 5, 7. Then we know its cofactor matrix Cij. The sign we can substitute before that, that is plus, minus, minus, plus. This we have already learnt in the previous video, that we can substitute the signs first and then we can put the values of the minors. Then the minor of 2 here is 7, that of 3 is 5, that of 5 is 3 and that of 7 is 2. Then the adjoint of A will be the transpose of Cij, and that will be 7 minus 5 minus 3, 2. Like this we can find out the adjoint of a matrix of order 2 into 2. Let's learn finding the adjoint of a matrix of order 3 into 3. To find the adjoint of a square matrix of order 3, suppose we have a matrix A, the elements in which are 1, 4, 2, 3, 6, 5, minus 1, minus 2, 7. First we have to find out its cofactor matrix. So we write cofactor matrix of A, that is suppose Cij as we write, And as I have already told you earlier, also we can take the signs of all the 9 elements for cofactors. So this will be plus, minus, plus, minus, plus, minus, plus, minus, plus. And now we have to take the values of the minors of all these 9 elements. For the element 1, this is 6 7 are 42 plus 10. This will be 52. For the second element 4, this is 21 plus 5, that is 26. For the third element we have minus 6 plus 6, that is 0. For the first element of the second row, we have 28 plus 4, 32. Second element 6, we have 7 plus 2, 9. Third element we have 5, this is minus 2 plus 4, that is 2. For this element of third row, we have 20 minus 12, that is 8. For the second element of this, we have 5 minus 6, this is minus 1. And for the third element, we have 6 minus 12, that is minus 6. By simplify, we are getting here 52 minus 26, 0. Minus 32, 9 minus 2, 8 plus 1 and minus 6. Now to find out the adjoint of A, adjoint A will be the transpose of Cij, which is interchanging the rows and columns. 52 minus 26, 0. Minus 32, 9 minus 2, 8, 1 minus 6. This is the adjoint of this matrix A. Like this we can find out the adjoint of a matrix of order 3 into 3. We discuss now some of the properties of adjoint of a matrix. And the first one of them is A into adjoint A is equal to adjoint A into A is equal to determinant A into I for any square matrix A of order n into n, where n is greater than 1. To find the verification of this, suppose we have a square matrix A having the elements A11, A12, A13, A21, A22, A23, A31, A32, A33. Then we know that the adjoint of this matrix A will be A11, A12, A13, A21, A22, A23, A31, A32 and A33, where these are the cofactors of all these 9 elements. If we find the multiplication of A with adjoint A, that will be A11, A12, A13, etc. into adjoint of A. Now we know that matrices are multiplied by row to column. If we multiply the first row to first column, we know that the product of the elements of any of the row with their cofactors, the sum of them is determinant A. But if we multiply the elements of any of the row with the cofactors of any other row, then that is 0, so it will be 0, and the same way this also will be 0. For the second row to first column, this is 0. Second row to second column, this again we find will be determinant A, and this second to third will be 0. Then the third row to first column will again be 0, and the third row to second column will be 0. Third row to third column again will be determinant A. Now can we have determinant A as common from this? This will be 1 0 0 0 1 0 0 0 1, which is the identity or unit matrix. So we can write this is determinant A into I. Similarly, we can also verify the second one, that is adjoint A into A also will come as determinant A into I. The second property for any of the square matrix A is that determinant of adjoint A into A or determinant of A into adjoint A is equal to nth power of determinant A if the order of A is n. For the verification, suppose we have a square matrix A that is of order 3 into 3. Just now we learnt that adjoint A into A or A into adjoint A is given by determinant A 0 0 0 determinant A 0 0 0 determinant A. If we find the value of the determinant of adjoint A into A or determinant of A into adjoint A, will that be equal to determinant of determinant A 0 0 0 determinant A 0 0 0 determinant A? We are getting determinant A from all the three columns or all the three rows. So will it come as determinant A cube into 1 0 0 0 1 0 0 0 1? And that is equal to determinant A cube into 1, or we can say determinant A cube. It means for order n into n, the value of this will be nth power of determinant A. The next property is that the value of the determinant of adjoint A is equal to n minus 1th power of determinant A. We can see this second property is telling us that adjoint A into A, determinant of that is equal to determinant of A power n. We can write this as determinant of adjoint A into determinant A is equal to determinant A power n, because we know that determinant of A into B is equal to determinant of A into determinant of B if A and B are non-zero matrices. And then by dividing this determinant A here, we are getting determinant of adjoint A is equal to n minus 1th power of determinant A. Let's learn about the singular and non-singular matrices now. Suppose we have a square matrix A. Let A be a square matrix. If we find that determinant A is equal to 0, then we say that A is singular matrix. For example, suppose we have a matrix A that is 2 6 3 9, then determinant A is equal to 2 6 3 9, which is 2 into 9 minus 3 into 6, 18 minus 18 is equal to 0. It means A is singular matrix. Now if we find that determinant A is not equal to 0, then we say that A is non-singular matrix. For example, suppose we have a matrix A, the elements in this are 3, 5, 4, 2. Then we find determinant A is equal to 3, 5, 4, 2, which is 3 into 2 minus 4 into 5, that is 6 minus 20 or minus 14, not equal to 0. And then we say that A is a non-singular matrix. Inverse of a square matrix. We have already learnt about inverse of a square matrix in the previous video. that is inverse of matrix part 1. And also we have learnt how to find out inverse by using elementary transformations. Here we will be learning how to find the inverse of matrix by using adjoint and by using polynomials. See, first we revise the concept of inverse, that is we have A and B, any two square matrices of same order such that A into B is equal to I is equal to B into A. Then we said that B is the inverse of A and represented as A inverse. Now when we want to find out the inverse of a square matrix by using adjoint, we are to remember one of the property which just now we have learnt, that A into adjoint A is same as adjoint A into A is equal to determinant A into I. And A is a non-singular matrix, means determinant A is not equal to 0. Then what we find? If we take the left hand side here, A into adjoint A is equal to determinant A into I, and multiply on both the sides by A inverse, will we find A inverse into A into adjoint A is same as determinant A into A inverse into I. We know that A inverse into A is equal to I. So we can write here, this is I into adjoint A is equal to determinant A into A inverse, because A inverse into I is A inverse. I into adjoint A is adjoint A. And we also know that determinant A is a numerical value, that is a number. So if we divide both the sides by determinant A, will it give us that adjoint A upon determinant A is equal to A inverse. It means this can be applied as a formula to find out the inverse of a square matrix, the adjoint of A to be divided by determinant A. And here we can see, if determinant A is equal to 0, means A is singular matrix, then can we say that A inverse will exist? No. So we say A inverse does not exist. It means to find out the existence of the inverse of a square matrix, we can see whether it is singular matrix or non-singular matrix. A inverse will exist only for the non-singular matrix. Now suppose we want to use the polynomial. Using polynomial, suppose for a square matrix A, let A be a square matrix, and it is given that A square plus A into A plus B into I is equal to 0. This is a polynomial in terms of A. We can find out A inverse if we multiply both the sides by A inverse. So if we multiply A inverse, do we find it will be A inverse into A, because A square can be written as A into A, plus A into A inverse into A, plus B into A inverse into I is equal to 0 into A inverse is 0. We know that A inverse into A is I. So it will be I into A plus A into A inverse into A is I. And plus B into this is A inverse into I is A inverse, and that is equal to 0. By transposing this, can we find that B into A inverse is equal to minus A into I and minus A. It means we can find out A inverse by 1 upon B into minus A into I minus A. This is the way any of the polynomial is given to us. Using that we can find out A inverse, that is inverse of the square matrix. We discuss one example to find out the inverse of a square matrix by using adjoint. A square matrix A has been given here, we have to find out its inverse. First of all, what we will do, we will find out the determinant of it. The determinant of it is, if we expand it along row 1, first element is 0, so 0 into something will give 0 only. Minus 1 for the second element, we are getting this as 1 minus 9, that is minus 8. Plus 2 into, this is 1 minus 6, that is minus 5. So this comes as 8 minus 10, that is minus 2, which is not equal to 0. And if determinant A is not equal to 0, we can say A inverse exists, because it is a non-singular matrix. And now we can find out the cofactor matrix of A. As I told you that first we will put the signs plus minus plus minus plus minus plus minus plus, and then we have to find the values of the minors of all these 9 elements. After finding these values, when we simplify, we are getting this as minus 1, 8, minus 5, 1, minus 6, 3, minus 1, 2, minus 1. Can we find out the adjoint now from this? We can write, therefore, adjoint A is the transpose of Cij. That will come as minus 1, 8, minus 5, 1, minus 6, 3, minus 1, 2, minus 1. To find out the inverse of A, we know the formula now, adjoint A upon determinant A. So can we write this as minus 1 upon 2, because determinant A is minus 2. Adjoint A is this, minus 1, 1 minus 1, 8 minus 6, 2, minus 5, 3 minus 1. If we multiply each element by minus 1 by 2, will it give us 1 by 2, minus 1 by 2, 1 by 2. This is minus 4. This will be plus 3, and this will be minus 1. This will come as 5 by 2. This is minus 3 by 2, and this will be plus 1 by 2, which is the inverse of the matrix which is given to us, that is A. Now we discuss one problem on the polynomial of matrix and how to find out the inverse from this polynomial. We have been given a matrix A, the elements in which are 3, 2, 1, 1. We have to show that A square minus 4A plus I is 0, and hence using this we have to find out A inverse. For the solution, what we do, we write the matrix which is given to us A, that is 3, 2, 1, 1. Then we find A square, and we know that A square is A into A. So we write here 3, 2, 1, 1 into 3, 2, 1, 1. And we know that matrices are multiplied from row to column. So this will be 3 into 3, 9 plus 2. This is 6 plus 2. This is 3 plus 1, and the last element is 2 plus 1. So this comes as 11, 8, 4, 3. Then we will go for finding 4 into A. That is 4 into 3, 2, 1, 1, and we multiply 4 to every element of it. That is 12, 8, 4 and 4. Now we find the value of A square minus 4A plus I. A square 11, 8, 4, 3 minus 4A 12, 8, 4, 4 plus I 1, 0, 0, 1. And this gives us 11 minus 12 plus 1, 8 minus 8 plus 0, 4 minus 4 plus 0, and 3 minus 4 plus 1, which is equal to 0, 0, 0, 0. It means this is equal to 0. Now to find out A inverse, we will multiply A inverse on both sides of it, and this will give us A inverse into A minus 4 into A inverse into A plus A inverse into I equal to 0, because A inverse into 0 is 0. Are we getting from here I inverse into A? We know is I, so this will be I into A minus 4 into I and plus A inverse, that is equal to 0. Are we getting the value of A inverse from here? That is 4I by transposing minus A, because I into A is A. And then we find here 4 into I means 1001 minus A means 3211. This is equal to 4004 minus 3211, and the answer comes as 4 minus 3 1 minus 2 minus 1 and 3, which is the value of A inverse. So like this, by using the polynomial also we can find out the inverse of a square matrix. In the next video, we will learn to find the solution of linear equations by using matrix. Thanks for watching my video. If you have any comments or doubts, leave them in the comment box and I will get back to you.